Hi class, this is a short lecture that is mostly a review of facts from pre-calculus that again you might not have used for a little while, but they'll have a couple important applications to calculus. And it's about inverse functions. So what we want to do is define the inverse function, and you should all already know this, but again, it's a useful refresher. So we can define the inverse function algebraically. If we have a function y equals f of x, then the inverse function is basically it's the function that undoes f of x. So if you compose the two functions, g of f of x, you get back the original input x. And this should work both ways. So in other words, if g is the inverse of f, then f is the inverse of g. And the usual notation is to use this -1 exponent. And again, you probably heard this a lot last year, but this -1 exponent does not mean dividing by, right? It's a function inverse, not a multiplicative inverse when it's applied to a function. Okay, so we want to notice a couple of things that are important. If f is an inverse function, then it must be 1-to-1. 1-to-1 means that two different inputs will always give a different output. So, for example, if you have the function has the same value at two different points, then, well, by definition, if it has an inverse, then f inverse of f of x1 is just x1, but also f inverse of f of x2 is x2. But if f inverse is a function, then, well, if I use the same input twice, I should get the same output. So the only way this can happen, if we follow the train of equalities, is if x1 equals x2. And that means that, yeah, the only time you have the same output is if you happen to have the same input. It's a 1-to-1 function. Oftentimes, if you don't have a 1-to-1 function, we restrict the domain of f so that it is a 1-to-1 function, and then we define an inverse. You had to do this when you defined the inverse trig functions, for example, and even all the way back to the square root function. Square root is supposed to be the inverse of x squared, but x squared is not 1-to-1, so first you restrict the domain and say we're only going to look at positive numbers. Okay, the other way you can think about finding an inverse algebraically is by solving an equation. Instead of writing y equals f of x, we write x equals f of y and try to solve for y. So for example, if you cannot solve the equation, then the function does not have an inverse, or at least it might not have an inverse if the solution is not unique. So for example, again, we'll look at this one. If f of x equals x squared and we try to solve x equals y squared for y, then y has two possible solutions. It's plus or minus the square root of x. So we have to restrict the domain of the original function and say that x has to be a positive say that x has to be a positive number, so that y also has to be positive, and then we'd get just the positive square root. Now we can also talk about the graphical inverse. If you draw a graph of the function, then you can reflect the graph across the line y equals x to find the graph of the inverse. And point by point, that just means you're going to flip the order of the points. All right, if you had c comma f of c on the graph of the function, then flip it, f of c comma c is on the graph of the inverse. And so you guys all remember the vertical line test. If you have a graph, it is the graph of the function of a function, as long as no vertical line intersects the graph more than once. And, well, the reflection of a vertical line is a horizontal line. So if the graph of the function intersects any horizontal line more than once, then when you reflect it, it won't be the graph of a function. So we can call that the horizontal line test to see if a function is 1-to-1. And just to look at an example here, let's take a rational function. F of x is 2x minus 4 over x plus 3, and I have the graph given also, so we can see a couple properties of the graph. There's a vertical asymptote here at x equals equals minus 3. There's a horizontal asymptote here at y equals 2. There's an x-intercept at x equals 2, and there's a y-intercept at minus 4 over 3. All right, and if we want to graph the inverse, y equals f inverse of x, basically any feature you have, you can just flip-flop the x and the y. So I had a horizontal asymptote I had a horizontal asymptote at y equals 2. That means I'm going to have now a vertical asymptote at x equals 2. I had a horizontal asymptote, I had a vertical asymptote at x equals minus 3, means that I now will have a horizontal asymptote at y equals minus 3. And again, the intercepts will also flip. So my x equals 2 intercept flips to a y equals 2, and my y equals minus 4/3 flips to an x equals minus 4/3. And with all that information, the basic shape of the graph is just a reflection, so it's a congruent shape. And, something like that. If you wanted to find this inverse algebraically, you'd have to start down writing the equation like x equals 2y minus 4 over y plus 3, and solve for y. So I'm going to have xy plus 3x equals 2y minus 4, and put all the y's on the left-hand side, and then factor out. So I have y times x, and then y times minus 2, and that should equal, move the 3x to the other side of the equation, solve minus 3x minus 4. So y should equal minus 3x minus 4 over x minus 2. And if you know your rational functions pretty well, you can easily see all the features that we already graphed. The vertical asymptote at x equals 2, the horizontal asymptote at y equals minus 3, the x-intercept at minus 4/3, and the y-intercept at 2. Yeah, you can see all those features. Okay, so let's apply this to calculus. We want to talk about tangents. We want to talk about derivatives. So if I have a curve, let me just draw this again. I don't like that curve. If I have a curve, I have some point on the curve, and I have a tangent line on that curve. When you reflect it, then the tangent line will now have a slope 1 divided by f prime of c. I'll draw a picture of that in class, I think. I don't think I have enough room on this slide. So algebraically, if you want to find a derivative of an inverse function, we can use implicit differentiation. So this is a very useful trick. Suppose I know a lot about the function f, but I don't know much about the function f inverse. All right, I can rewrite this equation by taking f of both sides of the equation, and now I can take a derivative and taking an implicit derivative using the chain rule. The derivative of f of y is f prime of y times dy dx, and the derivative of x is just 1, and so I can solve for dy dx. And again, if I want to write it just in terms of x, this f inverse of x, this is y, but rewritten just in terms of x. Looks like an unwieldy expression, but for some functions it'll be really easy. And our first application here is going to be to the exponential function. So in class, we defined the number e such that log of e equals 1, and we found the property that log of something raised to an exponent, I can take the exponent and bring it outside to be a coefficient. So we proved using the integral definition of log, that log of e to the x equals x. And that's another way of saying that these two functions, log x and exponential, are inverse functions. So now we can do calculus with exponential because it's inverse of a function we know how to do calculus with. So y equals e to the x is the same as saying log y equals x. Take a derivative, just like on the last slide. Derivative of log is 1 over y times y prime, and that should equal 1. So solve this equation. Dy dx, or in other words, the derivative of exponential function, equals just y, but y is e to the x. So e to the x is a very nice function for calculus. When you take a derivative, nothing happens. In fact, e to the x is sometimes defined using this property. E to the x is the function that when you take the derivative, you get back the same function. So, okay, so the next topic will be looking closer at the exponential function and trying to do some problem solving, refreshing our memory of pre-calc, and also using calculus. All right, that's it.